Okay, good morning. Thank you, Marion. It was very interesting, and I think we should really merge our knowledge on this, because I was thinking about, sorry, I'm doing this, about our experiments, for instance, when we do seismic experiments in towns, or so we should really go to the participatory approach to share the knowledge, but also to involve population and to do better science, actually. So now I'm talking about the seismic crisis management from a seismological point of view. So I will speak about seismic hazard, but from seismological, and not from, or with some clue in the effect on the society, on what we do. So I'm working at the INGV, which is a research institute in Italy, dealing with geophysics and volcanology. And I used to study the seismic source, and but now I'm on the site effects part, which is really how the shaking is affected by the surface geology. So it has a lot of impact in the perception and in the seismic risk as well. I'm also dealing with the seismic survey and the emergency team during seismic crisis. So what I'm talking to you today is what seismology is doing on earthquake hazard, in very quick, of course, a short list, and what is a seismic crisis and what we do during that. With some example from a recent earthquake, not so recent now, but the last large earthquake we had in Italy, which was in 2016. And we had a long seismic sequence with a maximum magnitude 6.5 that for Italy is very large. Not for other countries, but for us it's quite large. So many of you already knows that seismology is a young science. So just one, I don't know, at the beginning of 19th centuries, 20th centuries. So they just start to think that the earthquake were caused by faults. So it's a recent science. But however, it's a worldwide phenomenon. So in every country, almost every country, we experience earthquakes. And there are many variables and scarce knowledge, because everything happens below the surface, and several kilometers below, to hundreds of kilometers below the surface. So it's very difficult to understand what the physical mechanism and what is happening in this complex hidden world. There are different time scales and irregular phenomena. So this is another big issue. We have extremely slow deformation, which is charging the seismic fault, and slow means decades, but centuries or millennium also, but at the same time there are phenomena which are very fast, like when there is an earthquake. We have in few tenths of seconds, so we have a delivery of a huge amount of energy. There is a lot of uncertainties on seismic sequence evolution. So you can have this, for example, is a seismogram of one velocimeter, one sensor during this seismic sequence in 2016. So you see each line is half an hour. So before the first main shock, which is here at 3 in the morning, we didn't have so much seismicity. or at least it was a normal seismicity, so some small earthquake. But then suddenly there was this magnitude 6 in Amatrice.
It's just sorry because
what's wrong? Okay. But there are situations where there are foreshock before, so you have seismicity before a strong shock. Qu'est-ce que tu as fait? Parce que là, I cannot move. Maybe here? No. Okay. Okay, there is also another factor that you can have many main shocks and many aftershocks. This is the seismic sequences, the Central Italy seismic sequence. So you have the first, let's say the blue one is the first main shock, and then after a few months, the seismicity moved to the north with the strongest main shock of the sequence, and then so the seismic sequence was evolving in a different way, which we didn't expect. There is another strong impact beside the scientific interest, which is the large damages that we have during a strong shaking. These are examples of damages in the epicentral area, and as you can see, it could be very large. And I'll show you later on that is also due to different type of construction that we have in Italy in the mountain area. So there is a large social impact for earthquakes, large earthquakes. So here you can see the distribution of earthquakes since the last millennium that caused more than 10,000 deaths, and of course is mostly related where the population is concentrated. So what we know about what we do about the seismic hazard. I'm giving you the example of Italy, of course, but it could be extrapolated to other countries. So before an earthquake, we do the seismic monitoring. So we have a large network of sensors, more than 400 sensors, which we can locate the seismicity, and to your right you can see the 1 year of seismicity in Italy. Of course, most of them are a small magnitude earthquake, but we have several more than magnitude 4 earthquakes, and almost every 10 years we have a largest main shock. We with this seismic network, we do seismic and tsunami surveillance. So we have a seismic room where we have people working there 24 hours a day and 7 days a week. We share the data on a European platform, so the data go directly to open platform where everybody can download it, and we alert. Actually, this service is funded by the Civil Protection Department, which is alerted by the colleague in 2 minutes after the automatic location, and then in 30 minutes we have to give the final location and definitive information on it. This data, the location data goes directly on the web. So we have continuous data on the European platform and location data on the web as soon as there is a definitive location. And there are also, I will show you later, there is also, it goes also to Twitter, well, X now, and other kind of social media. As well, we work on the probabilistic seismic hazard map, and this is a law in Italy that the building code has to take care of the information that you get from the probabilistic hazard map. So this is a long-term project. Of course, now they are revising the map, which was delivered 20 years ago, this one. So it gives you the information about the acceleration that can be exceeded in the specific area. There is also another way of studying before a strong earthquake, which is the short-term forecast. There are several fields dealing with this, and one of these is the precursors. The problem of precursors is that you have to forecast time, location, and energy without any uncertainties, or at least and this is difficult because you have to find precursors that are always and solely related to the earthquake, so which is not straightforward. So it's very interesting, but not applicable nowadays. And we have, so I was mentioning, we have social media and blog, information campaign, activity with the generic public. But of course, it could be done not in, so it's not nothing. I was not thinking another thing. Anyway, so we try to inform about what we are doing, about the information that we can get. Something changed when there is the seismic emergency. So here I'm giving you the definition of what we consider a seismic emergency, but of course the civil protection can alert from whenever they want, if there is, even if there is a small earthquake which had a strong impact in the population, so they can just increase the alert. But for us, for our institute, whenever we have a magnitude more than 5, we enter in the seismic emergency period. And this is also related to potential tsunami in the Mediterranean. And in this case, the president will deem to have this emergency going on. So in this case, we focus in the spatial distribution of the ongoing activity. We try to figure out possible scenarios, and we do intervention in epicentral area with the emergency team. And we also manage the requests from the population, from the public, and from also the local authorities, of course. So this is what I was mentioned. There was this long sequence which affected I don't know, this is at least 100 kilometer high, and so it's a large portion of the territory. And in this case, we had many task forces which went on the field, which are organized before, of course, the emergency. So we have, this is I'm going through, so we have this one, which is related to mobile seismic networks. So they go in the field and put new instrumentation to better localize the seismicity going on. And here you can see how many stations we were able to put. And there is another task force which is called QUEST. They are doing microseismic survey. So they go into the field and look at the damage they had. This is an image of the Amatrice, which was the village that was totally destroyed after the first main shock. And but so in this case they have just to see that it was destroyed, but in many other cases they verify the different type of damage that there was, and they assess the macroseismic intensity for the area, which is useful for deciding the first intervention in the epicentral area. There is another task force which is called Emergeo. They are doing they are studying geological effect right after the earthquake. So here you can see the fault plane of exposed fault, and the 25 centimeter is the displacement after the first main shock, the magnitude 6 in August 2016. And but after the largest main shock a few months later, they observed a displacement of more than 2 meters on the same fault. This is not only co-seismic, is also some displacement of the ground above the fault, but it's still quite amazing. And there is also this other group which is called Emercito, which I belong to, and we are going and study the local seismic response following damaging event, and we are also engaged in a microdonation study to decide where to build the new settlement after the earthquake. And we do media think on our institution, and also with the university involved and other research institute in Italy. All this effort is very useful to understand the physical phenomenon which is going on, and to be better prepared to the next earthquake. This is just an example. I'm showing you 2 examples of what is improved after all this effort. So I don't know if it's clear, but all these dots, small dots, are the seismicity of the seismic sequence, and you have a section. I don't know if I can. No, I cannot show it. All the dotted line are section. If you look at the one below the F box, it's like a slice in the earth. And if you have this dense network, you really can follow the seismicity on fault planes. So this is a large improvement for us, that we can identify the faults which were responsible for the strong shaking. And it's very, and we can verify that the situation is very complex, because as you can see from the other section, so you have many faults in different directions. So several years ago, we were thinking that there was one fault giving a large earthquake and that's it. But now that the knowledge is going on, we discovered that it's more complex than, of course, than we expected. And also in my field, there is a large impact on the study of differential responses in small areas, and this can affect the choices of the municipalities on the settlement. There is also another big source of information, which is how the damage behave. And this is an example of cumulative damage. We had 3 main shocks during the sequence. So the first main shock didn't affect very well this building, but then the second and the third one was really affecting. So this is also an interesting input for engineers because they really understand how buildings behave, which is not straightforward because there are not other way to see what happened to or existing buildings. And also it's interesting to see the role of materials that this is our typical way of building, type of buildings in central Apennines and the mountains, and so it's really interesting, and it's really interesting because you can understand what happened and then retrofit in a proper way. However, so it's scientifically it's very interesting whenever we have an earthquake, but then there are many issues arising during a seismic emergency. First of all, the public attention increases, of course, in the epicentral area with this, but outside the epicentral area, there is a strong interest on the topic, which is not the case far away in time from earthquake. I mean, after months, you don't care anymore. And but also linked to this, there is a misconception of building safety, and also a low perception that large earthquakes occur in your backyard. And during a seismic emergency, any scientific information become risk communication. So it changes everything. Whenever we speak in our normal life, people care about the situation, but it's not a problem. But if there is an earthquake, and we have to be really careful on what we are saying, because everything is perceived in a different way. And there are also many actors to deal with us, which is not the case in our scientific life. So we have the public, they need for reassurance, which is we are not really able to deal with this, and they look for answer to practical issue, which is not, they really don't care about the details on the fault plane or whatever, but they want to know what they have to do. The mass media looks for simplicity and certitude, which is not, we are not able to give this kind. We usually give very complex information because the reality is complex, and it's impossible to have certitude in this field. They also search for sensational news, and another issue is the speed of information, which is very good in some cases, but in this, for risk management, is not always easy to manage, because whenever there is an information going on about an alert or whatever, it's very difficult to go back and to recover the wrong message. On the other side, on our side, the scientific community cannot give absolute certitude, and we have to show that there are a range of validity of what we are saying. So it's not one answer, but we have one answer and a certain uncertainty. That also we have scientific theory, which could be just a part of the reality. So there are many different theories, and is not always we cannot always explain everything with a single theory. Actually, another issue I'll show you. Oh no. Is the strong earthquake with low probability of occurrence is not zero probability. And this is a huge issue, at least in Italy. I don't know in your countries, but whenever we speak about low probability, the perception is that, okay, well, there is no problem. But even if there is 0.001% of probability, if you have an earthquake, it's a big deal. It's not that it's raining. Let's see. Other problematic issue, what I was mentioning yesterday, and I realized that is really country driven, is the legal involvement. So in Italy, but also in New Zealand, we have two cases. One for the L'Aquila earthquake in 2009, and for New Zealand and White Island for the White Island eruption. So everything is related to the warning. So wrong warning to the population, and this is also that could go through trials toward scientists. So that's why I was mentioning, because there was a wrong alert. Somehow, I'm just making the story short, but if you are curious, I can explain you better. So in both cases, scientists were at the end they were not convicted, but they had to go through a trial. Okay. The other issue is what I was mentioning, the uncertainty and threshold alert. So this is a case of volcanic eruption, but it could be applied also during the seismic sequence. So you have several parameters to monitor, and if there is an increase of this value, you can go through a level of alert. But after this, you can have, so there is a decision window where you have to say, okay, maybe we are going through an eruption, or maybe we are not going through an eruption. And after this, but you can have several situations. So there could be an eruption. So maybe if you gave the alert, that was a good things to do. But you can go also back to the normality. So it's not that we are the uncertainty of the natural phenomena, because there is a scarce knowledge, is very large, or you can have a steady state, so it never goes to the eruption or go back to normality. This is the same for the seismic sequence. So it's very difficult to give this kind of information devoted for decision maker. So this is all related to decision maker. So it's a really this participatory way of thinking should involve the decision maker as well. These are already another point that I want to tell you is about the user language that we have as a scientist. So these were 3 examples of terms that we use. For example, normality, that for us is really related how the data are distributed. So normality could be perpendicular or with a Gaussian distribution, or ordinary. For example, normal activity for us is that there are earthquakes. So this is kind of normal. In a common sense means there is a usual. It's usual, not is not Gaussian or whatever. But evidence for us is less than a proof, but for the common sense is a certainty. So it's evident for a common sense. So whenever we describe the seismic sequence to the public, it's really difficult to really explain them what is going on with our kind of language, specific language. And error, this is the other main, which for us is intrinsic to any measure. So it's normal that if you measure something, you have an error, but for the common sense is a mistake. So really, whenever we enter in the risk area, everything is changing because we talk with other community which understand in a different way what we are saying. That's it.